All right, kiddos. So I wanted to show you for today's work. Today is Tuesday, March 24th. We're doing lessons 410 and 411, I think. Yeah, 410 and 411. So I wanted to show you a couple of things, but if I share my screen, it lags too much on your end. And so I'm just making this recording to deliver the lesson for today because I can record it and there won't be any lag and you can see in real time what I want you to see. So 410 is all about how heat energy, not temperature, but heat energy changes or is used during changes of state. So we're going to examine the heating of ice. And basically what you're going to do is we're going to go through the lesson 410, and there's some really neat little animations to show you how much energy is needed to be put into a system to make the system go from being ice to liquid to gas or water vapor. You're already familiar with this. We did this, back in States of Matter at the beginning of the semester. This is not new, but I just want to review real quick. So we have a beaker of ice water. It's really cold. It's starting out at negative 50 degrees Celsius here. And I'm going to click play. We're going to heat it up. And what you'll see on the graph is you'll see the phase change, or the heating curve is what you're going to see. So just keep your eye on the graph over here, and you can see that the temperature's going up and up and up. Now, at some point, right, because we're heating it up, you see the flame down here. When the temperature gets to 0 degrees Celsius, that's the temperature where ice melts, right? Water freezes. You're not going to see this line go up anymore. So that we have temperature here on the y-axis. So the temperature is going to stop going up when the system gets to 0 degrees Celsius. At that point, you're going to start to see the phase change. The line is going to level out, and that's where the phase change happens from ice to liquid. Because remember, as we add heat energy to this system, the energy can only do one thing at a time. It can either raise the temperature or change the phase. You can't do both. So what you'll see is this line start to level off, and you'll see this change from ice to water, liquid water. And by the way, along the x-axis here is time. So you can see the ice changing to water. That's just a stir bar right there spinning. It might be a little hard to see, but you can see this blue line leveled off at 0 degrees. And it'll keep progressing. The temperature will stay the same until the ice turns to completely to water. And at that point, once the phase change is over, now we have just liquid water, the energy can be used to raise the temperature again. So that'll keep going. The temperature will keep going up. You can see the temperature of the water rising. It's liquid water. And when it gets to 100 degrees Celsius, it should boil, right? Or start to boil. At that point, during the phase change, you should see the line level off again, and it is. Because again, this heat energy that we're adding to the system can't do two things at once. It can either raise the temperature of the system or change the phase. Can't do both. And so now the water is boiling, and so this is a phase change from liquid to gas, and so the line has leveled off. So I just wanted to remind you that at where the lines level off, that's the actual time of the phase change. This one here is when the ice is changing to liquid water, and this is the liquid water changing to gas. So we're going to go through the same thing in lesson 510, but instead of just watching the line go up and over and up and over, we're going to add some numbers to it. Okay, so we are going to take part in an experiment where we will follow the heating of a 100-gram block of ice from minus 100 degrees Celsius, which is cold. Remember, water freezes at 0 degrees Celsius. So from minus 100 degrees Celsius all the way to 200 degrees Celsius. So we're going to go from really cold to really hot. And so this is our system. We have a beaker, it's got a lid on it, a thermometer in it, right? We've got this nice closed system. No air or heat, no energy escaping, no energy getting in. And it's on a hot plate. So we're going to heat it up. And I'm going to press play, and what you're going to see is this block of ice. There's nothing but ice in here right now. You're going to see this block of ice start to heat up. Okay. So what we can do with that is we can actually measure the amount of heat that went into this system from the hot plate. So the amount of heat that was transferred from the hot plate to the ice to get it to a higher temperature. It hasn't melted yet. Notice it hasn't melted yet. All we're doing is raising its temperature. So it started at minus 100 degrees Celsius, right? Here it is right here. We started at minus 100 degrees Celsius and we raised the temperature up to 0 degrees Celsius. So how much energy did that take? And right here we can do it. It says use our normal formula Q equals mc delta T to calculate the heat change. And then it gives us the specific heat of ice, which is our C in the equation. So all we have to do is plug in the numbers. So that's what this crazy mess is. I don't want you to be afraid of looking at this. I want you to see what this is calculating. So this is heat equals mass times specific heat times the change in temperature. The mass of the ice is 100 grams multiplied by the specific heat of ice, which they gave us down here. So 2.05 joules per gram degree Celsius. That's not a minus sign. Times the change in the temperature. The temperature went from negative 100 to 0. Okay, so it's a 100 degree temperature change. And then when you do all that math, you get 20.5 kilojoules, which is the same thing as 20,500 joules. I know we're used to working in joules. So it took 20.5 kilojoules of heat to raise the temperature of this ice from minus 100 degrees Celsius to 0 degrees Celsius. So the next thing we're going to do is keep adding heat, but at this point, because we're at 0 degrees Celsius, instead of raising the temperature, we're going to go through a phase change. Well, we aren't, but the ice is. And you can see the line was flattened out. We call this heat that is needed during the phase change from ice to liquid water, the heat of fusion. And we're going to use the equation Q equals mass times the change. This is supposed to be the little delta H symbol right here. See that little guy? For some reason it's a typo in the course. This should be the same thing. It should be a little delta H. So we're going to take the mass of the water, multiply it by the heat of fusion. That's what we call it, the heat of fusion. And we'll get the amount of energy it took to get from this point on the line to this point on the line. So we still have 100 grams of water. They gave us the heat of fusion, which is 334 joules per gram. If I do that math, I get 33,400 joules. So we had the amount of heat to get us to 0. We just calculated the amount of heat to get us through the phase change. Now we're going to switch back, because the phase change is over, we're going to switch back to raising the temperature. Okay, so when we raise the temperature, we can use our good old Q equals mc delta T again. We still have 100 grams of the liquid. We're dealing now with not ice, but liquid water, so we use 4.18 joules per gram degree Celsius for our specific heat. And our delta T again was a 100 degree temperature change. We went from 0 degrees Celsius to 100 degrees Celsius. No boiling yet. Okay, all we've done is raise the temperature of the water. If you do that math, you get 41.8 kilojoules, okay, or 41,800 joules. The next thing we're going to do is calculate how much energy is needed during the phase change of liquid to boiling, or to gas phase. And you can see we're in our phase change because of the flat line. The water is boiling off, and now we have nothing but a beaker of steam. Okay, we've boiled off all the water. So we call that process the heat of vaporization is the heat involved in a change from a liquid to a gas. So how much energy did we use here, right? So we're going to use that old equation, Q equals mass times the heat of vaporization. That's what this is standing for. That should be the little delta symbol right there. We still had 100 grams of water multiplied by the given. They gave it, you would find this information in a table, 2.26 kilojoules per gram. Multiply that, you get 226 kilojoules. So we had a certain amount of heat to get us from minus 100 to 0, a certain amount of heat to go through the first phase change, a certain amount of heat energy to get us up to 100 degrees Celsius, and then a certain amount of heat energy to get us through the second phase change from liquid water to a gas. As you continue to heat the system, the temperature increases to 200 degrees Celsius. Now remember, all we have in here is steam at this point. The kinetic energy of the water molecules increase, the molecules move further apart, and the water vapor expands. The specific heat of water vapor is 2.08 joules per gram degrees Celsius. So you can see the whole chart without anything in the way here. And then we're going to raise the temperature even more. We're going to heat up that steam and get it up to 200 degrees Celsius. It's a closed system, right? So the steam isn't escaping. So now we're raising the temperature of the steam. And of course that took a certain amount of energy. We had 100 grams to start. The specific heat of water vapor or steam is 2.08 joules per gram degrees Celsius. Multiplied by the 100 degree temperature change. We went from 100 degrees to 200 degrees. And that cost us 20.8 kilojoules of heat. If you add all of that up, you get the total amount of heat required to raise the temperature from 100 degrees Celsius to minus 100 degrees Celsius to 200 degrees Celsius. So if you remember, we had to input into the system 20.5 kilojoules per heat to get the ice up to 0 degrees. Then the phase change cost us 33.4 kilojoules. Raising the temperature up to 100 degrees Celsius cost us 41.8 kilojoules. To get through this phase change from liquid water to steam, it cost us 226 kilojoules. And then to get the steam up to 200 degrees Celsius, it cost us 20.8 kilojoules. So if you add up all of those different processes, the heating of the ice melting, the heating of the liquid water boiling, and the heating of the steam, if you add them all up, the total heat energy required to make this happen was 342.5 kilojoules. The next page in the lesson takes you in the opposite direction. Fortunately for us, we don't have to do the math again because we're using the same temperatures and we're using the same substance, right? H2O. So if you look, this was the calculation we just did, the total heat that we had to put into the system, right? We had to give the system had to absorb heat to get from ice to steam, was 342.5 kilojoules. It's a positive number. If you're going in the opposite direction, meaning you're cooling the system down, So to get from 200 degrees Celsius all the way down to solid ice at minus 100 degrees Celsius, you have to remove heat, right? We have to cool it down. So you just flip the signs. That's all you have to do. All the numbers will be the same, except instead of adding heat, this time we are removing heat from the system. So in, I guess, conclusion, a couple of vocabulary terms we went through. The heat energy during phase changes involves increasing or decreasing kinetic energy relative to intermolecular forces. The temperature does not change. So again, think of that flat line in the graph. When the phase change is actually happening, the temperature is not rising. Energy can't do two things at once. It can either raise the temperature or it can change the phase, not both. So the heat of fusion is what we call the energy needed to get from a solid to a liquid during the phase change. The heat of solidification is what we call the energy needed to get from a liquid to a solid. The heat of vaporization is what we call the heat needed to get from a liquid to a gas. And then to go from a gas back to a liquid, we call that the heat of condensation. And you can see the different symbols that are used to represent those, those terms. So I don't want you to be frightened off by these symbols. This is just the heat of fusion. This is the heat of solidification. This is the heat of vaporization. It's just delta H with a little V, with a little S, and a little F.